Sorry about jumping the gun there, Kirstine. So thank you so much for organizing this. I'm going to be talking about how we've been using the wetlands and water level data to look at trends in our salt marshes. And then Hillary is going to be showing you how we've used some preliminary results to address some of the degrading conditions that we're seeing in our marshes. So Hillary and I work in coastal Massachusetts on the south shore of Cape Cod, and this is the Waquoit Bay and the Sagelot Pond marshes located here. We have broken up our wetlands and water levels monitoring into three different sections, and I'm bothering to show you that because I'm going to be showing you some data from all three sections in the subsequent slides. I do want to call your attention to this section 3 or doghead marsh. Maybe you can see why we call it that, because we're going to be focusing in on that. It has some pretty degraded conditions. So I stole this slide from the New England Marsh Vegetation Synthesis Project. It is one of the first projects that I participated in when I came into the NERS system. And one of the results that we had was that when we pulled all the data from Maine to Rhode Island, those were the 4 New England reserves at that time, was we saw that there was a decline in flooding sensitive plant species and that there was an increase in the amount of water, bare sediment, and dead plants through time. And you can see this depicted in some of Kenny's plot photos from the Narragansett Bay Reserve. Another project that I participated in at the same time is the Setter project, and that was led by Kim Crespin, and I know she's going to be talking about that later. But she developed some really awesome scripts and data visualizations for people to be able to look at their surface elevation trends through time. And what you're seeing here are the results of all 10 of the SETs that we monitor, and the trend from the annual observations is shown in the blue line, and the red line is a long-term rate of sea level rise. So that red line is the same in all of these graphs. And hopefully what you can observe is that the blue line is below the red line, and so very few of our SETs are accreting in pace with sea level rise. And that is particularly noted in our section 3 or doghead marsh, where our accretion rates are really failing to keep up. Another project that I'm participating in, but is led by this stellar crew, is the National Salt Marsh Synthesis, where it's taking all the reserves monitoring data and putting it together and trying to develop some common ways to look at it and analyze it. And the top 3 categories for Waquoit Bay of all of our cover classes are unfortunately bare, dead, and Spartina alterniflora, which is a flooding sensitive salt marsh cordgrass. And the trend through time of decreasing amount of cover by Spartina alterniflora is particularly noted in the section 3 marshes. Here's a picture of that section 3 doghead marsh again. This is pretty old data from our habitat mapping program. We are currently updating these products. And what I want you to see here is that the red polygons are showing where there was a decrease in vegetation extent and an increase in pool extent over the 8-year time period shown in this change analysis. So we have a lot of red here indicating a loss of vegetation, increase in open water. Here's a picture of the doghead marsh from a different perspective, and you can see just how much water is impounded on its surface even when it's not high tide. So this is a marsh that we chose to try to address with some restoration techniques. I developed this list of potential restoration options just in general after observing some of the poor conditions in the doghead marsh. I do have to note that the removal of tidal restrictions has already been accomplished for this marsh 3 years before the wetlands and water level monitoring program started at Waquoit Bay. There was a box culvert put in, replacing an undersized culvert. And now Hillary will move on to telling you about runnel excavation, which is our current attempt to try to deal with that.
Great, thanks, Megan. So just a brief overview for those of you who don't know what a runnel is. These are very narrow, shallow channels that are dug on the marsh surface to connect an area of impounded standing water to a drainage feature, such as a mosquito ditch or a creek channel. And the goal of runnels is to help drain that standing water on the marsh and encourage revegetation. Next, Megan. There's been a number of successful runoff projects here in Massachusetts. This is a microtidal marsh in Buzzards Bay, and you can see within just about 1 year, they found extensive revegetation and drainage of that standing water. Next, Megan. Here's an example of a macrotidal marsh in Plum Island, Massachusetts as well. And so you can see that here it actually took much longer for that vegetation to regrow. It took about 7 years. And so the success of runnels can be highly site specific and dependent on initial site characteristics. Okay, next, Megan. So one of the questions that I am addressing is understanding how changing the water level on the marsh platform is going to change sediment oxygen conditions. And so we see that the impounded marsh areas have lower redox potential, as you might expect, with less flushing and drainage. Next, Megan. But runneling actually doesn't over increase the amount of available oxygen in the sediment. And so this is going to be really important when we're thinking about biogeochemical processes. Next. Specifically carbon decomposition. So this is an aerobic process. Organic matter is decomposed. Decomposition of organic matter is stimulated with more oxygen. And so if you just look at this center box here, the runneled plots are in light blue and the control plot, so the impounded water is in dark blue. We find that there's no increase in decomposition with the increase of runnels. So this is going to help the marsh maintain its carbon storage capacity. Next. And then the last result I want to show today is denitrification rates. So this is an anaerobic process, so it requires no oxygen to proceed. Denitrification is a major ecosystem service that the marsh provides by removing nitrogen back to the atmosphere. And so if we have over-oxygenating the sediment, we might reduce that denitrification rate. However, I found that this in the runneled plots, denitrification is actually restored back towards reference levels. So the marsh is able to continue removing nitrogen and provide that ecosystem service. Next. And so as Megan mentioned, Doghead Marsh is a pretty degraded marsh, and we identified 5 different pools that we thought would benefit from runnel in installation. And so here's an example here of pre-runnel on the left and post-runnel about 9 months later. You can see the extensive drainage that we've already seen thus far. Next. And here's just another example of a much more successful pool that has drained much more. And so if we look at the numbers, Megan, the low water level next, Megan, before runnels were installed was about 12 centimeters at low tide. After the runnel installed, that number has gone down next to 4.3. So the runnels in this pool are reducing standing water by about 66%. Next. So to conclude, next. Runnels are successful at effectively reducing standing water off the marsh and encouraging revegetation. And so far, we've seen that they will not disturb important biogeochemical processes because they're not drastically altering the redox potential of the marsh. And that's it.
You pulled it off in time. So you have time to answer one question, which is, did you base where you dug runnels on elevations from LiDAR or just by watching where the water was standing and not fully draining?
Yes, so we did not use LiDAR. We just targeted pools of standing water. And then to decide where we dug the runnel, we would sort of look just visually at the topography, and it's a little bit of a best guess as to where it was going to drain.
Excellent. Such an impressive, multifaceted analysis. And thank you for keeping us on time.